Hello everyone, my name is Dave Rahe. I'm here to talk to you about the Davis-Besse reactor head incidents. So this is a continuation from Marie's discussion on the actual design of the plant. So I'm not going to focus on that as much and do a quick overview. We're going to start off with the overview, of course, and then we're going to lead into the timeline events that led up to the incident at Davis-Besse. So first off, the overview is on March 6th of 2002. There was approximately a 24 square inch cavity discovered in the Davis-Besse reactor head next to the 3 control rod drive mechanism. The only thing holding back primary pressure was a 1/4 inch of stainless steel. The only thing keeping the reactor covered and all the pressure and temperature inside the reactor was a 1/4 inch of stainless steel. And this incident, from when the initial control rod drive mechanism cracked till they actually discovered it, went on 6 years from when they initially cracked and actually caused the corrosion from the through-wall leak. So when this occurred, NRC said, Davis-Besse, you're shutting down. They shut them down, and they stayed shut down for 2 years. And that's a lifetime in nuclear power. And you can see right behind me, this is the actual incident, the head itself. This is a cutaway of where the number 3 control rod drive mechanism was. It would fit in right here vertically. And then here's the 6 inches of carbon steel that got eaten away. And here's that 1/4 inch of stainless steel that actually was holding back the primary pressure. So here's another view of the reactor head itself, a diagram. And we're going to be talking about the flanges up here. These caused a lot of leaks initially in the plant itself, which they assumed was where most of the leaks were coming from, was right here at these flanges. And then here's the number 3 control rod drive mechanism, and where the actual void was formed was right here. So here's a flange, here's the insulation that goes through, and here's where the actual void was in the plant. So we're going to start off with the timeline now. We're going to start off between 1987 and 1989. The NUC issued 3 items. They issued 2 notices saying there's 2 separate plants that had boric acid put on their heads and caused significant carbon steel corrosion on their heads. So letting the industry know that other plants have had this issue. And then, at the last part of it, they issued the third. They issued a generic letter 88-05, which required every single site to institute a program for boric acid corrosion control, saying, hey, how are you preventing boric acid and how are you inspecting for it, preventing it? So we go on, they created their boric acid corrosion control program, and then they continue on. 1990, during their number 6 refueling outage, they went into inspections and they found there was boric acid on the head of the reactor. And it was coming from the flange on the control rod drive mechanism. There was a problem with the gasket. Even when they put the replacement gasket, even that leaked. It was a common cause with this type of head. And they're having problems with the inspection. They're going through these mouse holes, which are only 5 inches by 7 inches. So an engineer said, okay, I'm going to put a modification in to make these larger holes, viewing ports basically, on the side of the cover to inspect the top of the head better. And they issued it. They haven't done the work, of course. And then at this time, during 1990, the NRC also issued a warning to industry saying that Inconel 600, which our control rod drive mechanisms were made out of, are susceptible to primary water stress corrosion cracking, which could cause a through-hole leak. And at this time was when the investigation determined that between 1990 and 93, that the actual crack on number 3 control rod drive mechanism initiated between this time. So right when they issued this notification, they said, hey, we may have this leak. So they continued operation, we're doing good. They're in the next shutdown, and they're in the 7th refueling outage. They found excessive amounts of boron. They're like, whoa, there's a lot of boron on the head. They did an inspection, they found this popcorn, they called it. It was basically the boric acid came down from the flange, leaked on there, it fizzled, and made like a popcorn looking stuff out of the boric acid. And the heat of the head was at 550 degrees, which just caused it to boil away. So they thought it was okay because there was no mechanism of corrosion. They took the moisture away. But Westinghouse still issued a group to say, we still have issues with our reactor vessels from carbon steel corrosion due to boric acid. So they said, we still got to look out for this. Then, again, in 1993, during their 8th refueling outage, the manufacturers, the creators of the plant itself said, hey, we need to make sure we're in compliance with this head. So doing these inspections per the generic letter 88-5 will meet the intent as long as if you find a leak, you identify where it's coming from. And their spec was 1 cubic centimeter they identified. And everyone's like, okay. Remember that modification I told you about for the engineer? At this point, they voided it in 1993. They said, oh, we don't need that. And then during the same time, because there was so much boric acid leaking out from the flange, there was actually a problem with the reactor head vent line on the steam generator, which on number 2 steam generator, which actually caused corrosion and ate away part of the carbon steel on that. So this is their first incident where they see carbon steel corrosion from boric acid itself. And here's a view they were talking about for the cracks between the axial crack and circumferential crack on the control rod drive mechanism itself. And they're like, okay, we can do these inspections. They continue on. And then during the 9th refueling outage, they conducted another head inspection. Seems like a common trend, right? And they found more boric acid on the head. And they're like, okay, so how are we preventing this? How are we making the generic letter 88-05? What they did, they put a camera on the end of a broomstick and try to shove it up those mouse holes to do their inspections. They're like, okay, we're looking, we can't see it all, but we think it's good. So they did their visual inspection and said, okay, it's good. It's probably, there's no leak of the control rod drive mechanism is low, so we don't really need to do the inspection. It's not a commitment to the NRC. So we may not need to do this, and we're not going to. And the modification was reissued again, saying, hey, we really need these inspection ports. In 95, they looked at that modification and said, we're going to postpone it. We need a little more information before we allow this to go through. So that continued on. During the 10th refueling outage, they went in there, did some more inspections, and they found actually red boric acid at this point around the nozzle 67, which indicates there's actually corrosion, but that wasn't identified. The site says, we should have removed as much boric acid as we could, but because of the high temperature of the core, it won't really matter. It has no initiation on the boric acid itself. And even though now they have a second incident, on the reactor coolant pump 1-1, they had a casing leak from boric acid corrosion to carbon steel. There's so much boric acid in the air and containment, it's corroded another. That's the second incident with carbon steel now. Then 1997, inspection port was deferred till the 12th refueling outage. Like, we can push it off some more. We don't need it right now. And then again, the NRC issued another generic letter, 97-01, saying degradation of the control rod drive mechanism nozzle penetrations. Right, this is an industry issue. Many people are having through-wall leaks. Now we need to fix this. But of course, they did their inspection and thought that was good enough. And then again, during the 11th refueling outage, they found red boric acid again on the reactor head. This time it was clumping. So much boric acid was building up, they were seen all over the place. And they said, okay, well maybe we do need that inspection window, but let's push it off to the 13th refueling. We can't do it in the 12th. Let's do it on the 13th. And now we have a third incident with boric acid corrosion on carbon steel where the reactor coolant pump 2 yoke and bolt corroded due to boric acid. And right here we got a picture of that. You can see the significant corrosion on that yoke itself. Look, it just ate away at that carbon steel. When it has the mechanism, it eats it away very quickly. Then in 1999, they had a actual leak. The pressurized safety valve leak started following the startup. And they're like, oh man, our filter started to clog for our rad monitors, our containment air. And the reactor coolant pump leak rate went up to 0.8 gallons per minute. Our tech spec is 1 gallon per minute. So we're just under the tech spec. And our normal is 0.05 gallons per minute. So we're like, okay. So they did in 99, they did a mid-cycle shutdown. They shut down, they fixed the pressurized spray safety valve. They did the repairs and they started back up. And leak went up to went down to 2.2 gallons per minute, which is a lot better than 0.8, but it's a lot worse than it was originally of only, being approximately 0.05 gallon. It's 4 times that right now. And you can see here's actually the containment air coolers, where this is a clean one here on your left. This one on the right is actually corroded, or not corroded, but covered in boric acid. Significant amount. That's just in the air. 2000, during the 12th refueling outage, they did an inspection again. They found brown boric acid now. It's not red anymore, it's brown. So that means actual carbon steel is coming out with that through the weep hole. This is actually coming out of there. And they discovered solid deposits. They said, okay, well, we need to try to clean these heads and inspect them. So they closed out the notification saying, the startup assurance, we cleaned it, we had no more issues, and we didn't. What they actually did, they did a partial. They didn't do all the inspection, they did a partial inspection. And this is actually a violation of the 10 CFR, saying it's not the full truth. And here's where you actually see some of that corrosion here. This is actually coming out of the control rod drive mechanism. At the bottom, you actually see some of that brown. And then you can see it coming out of the mouse holes itself. Look at all that brown boric acid. That's a significant amount. Then in 2001, the reactor coolant leak rates kept on going up. They kept on increasing And they're like, okay, what's going on? So they created a team to try to figure out the issue. And in the same time frame, the NRC issued a bulletin to the entire industry saying, we've had so many issues with CRDM cracks, we need everyone to shut down by the end of the year and make sure you don't have them. Davis-Besse team, well, they went back and forth to the NRC trying to push it out, saying their inspections were satisfactory. Can we keep on operating until February of next year? So finally, after back and forth, the NRC approved it. The NRC approved operation until 2/16/2002, where when they did finally shut down, they found they were going through their inspection on the control rod drive mechanism with a camera going up inside the CRDM, and the CRDM actually tilted over. They're like, oh man, what's going on? So they kept them going. You can see the boric acid flowing out of this mouse hole. And there's a cutaway of the head itself. Again, you can see the significant amount of damage from the number 3 control rod drive mechanism. So think about that when you're going through this. So in closing, thank you for your time. I'm going to leave you off to Jeremy, who's going to look at the actual effects on the industry itself and how it's going even today. We still talk about it in nuclear power. Thank you very much for your time.